Swayam Prabha. Digital India. Educated India.
Welcome to lecture 38 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is One-Way Error Component Model with Fixed and Random Effects. In the last lecture, we have discussed different basic concepts of the panel data. We also discussed the advantages of panel data over cross section data and time series data. Now, suppose you have observations on you have panel data observations on a number of variables. Then one of your main objective may be to explain the variations in a particular variable called dependent variable on the basis of a set of explanatory variables. So, then again we would like to develop some model for explaining the variation in dependent variable using the explanatory variables. Obviously, the model involves some of the characteristics of panel data. The models which we are going to discuss in our lecture are actually different variants of usual linear regression model, but the panel data models differ from the usual linear regression model, or you have different kind of panel data models. We define different kind of panel data models. The difference between different panel data models is due to the assumptions about the disturbance term, the error term. In this lecture, we are going to consider the panel data models having one-way error component. We will consider both fixed effect model as well as random effect model. Now, first we consider the model, say yit equal to alpha plus xit transpose beta plus uit, t equal to 1 to capital T, I equal to 1 to n. So, obviously, we are considering balanced panel, and then x I t is of the form x I t 1, x I t 2, so on x I t k transpose. So, it is a k cross 1 vector. So, in all we have k covariates. Beta is k cross 1 vector of regression parameters having elements beta 1, beta 2, beta k. And then obviously, alpha is the intercept term and UITs are the disturbances. Now, we write this model using vector and matrix notations. So, suppose we write yi equal to yi 1, yi 2, so on yi t. So, corresponding to the ith cross section, we have stacked all the observations in yi, and then capital xi is equal to xi 1, xi 2, so on xik, then xi 2 1, xi 2 2, so on xi 2 k, and so on xi t 1, xi t 2, so on xi t k. So, this capital Xi is T cross K matrix corresponding to the ith cross section. This is the matrix of observations on all the K explanatory variables. For the U I is T cross 1 vector having elements U I 1, U I 2, so on U I T. Then we can write the model as y I equal to alpha L T plus x I beta plus U I. Here L T is T cross 1 vector with all elements equal to 1. So, this is L T. Further, we can extract the observations in the form, say we write y equal to y 1, y 2, y n. So, obviously, this y is n t cross 1 vector. So, now we have extracted the vectors of observations of all the cross sections. Then capital X is equal to capital X 1, X 2, so on x n. So, again capital X is n t cross K matrix, and we obtain this matrix capital X by stacking all the observation matrix corresponding to different cross sections. Then U is n t cross 1 vector, which is obtained by stacking U 1, U 2, U capital N. Then using these matrix notations, again we can express the model 1 in the form y equal to alpha L n t plus x beta plus u. Here L n t is again a vector with all elements equal to 1, but its order is n t cross 1. All the elements of L n t are 1. Or we can write the model in the form y equal to z delta plus u, where the matrix Z is defined as L n t x. So, the order of Z is n t cross k plus 1. It has n t rows and k plus 1 columns, and delta is defined as alpha beta. So, it is the vector of all the regression parameters including the interceptor alpha, and the order of delta is k plus 1 cross 1. Then different panel data models are variants of linear model. At least the panel data models which we are considering here are different variants of linear model. Then different models differ in their assumptions about the nature of disturbance term u. For different models, we take different assumptions about u. And then usually in panel data model, number of individuals is large and number of time periods is small. Now, we attempt to estimate the parameters of the model 1. So, first we consider the pooled estimator. We consider the model 1 and assume that UITs are IIT having mean 0 and variance sigma square u for all I and t. Then suppose you define the matrix Q and T equal to I n t minus 1 upon n t L n t transpose. This I n t is actually identity matrix of order n t, and if you consider this 1 upon n t L n t transpose, then what is L n t transpose? It is n t cross n t matrix with all elements equal to 1. And if we divide it by n t, then we get a matrix of order n t cross n t with all elements equal to 1 upon n t. Further, you can easily verify that the matrix Q n t is idempotent, because if you multiply Q n t by Q n t, or you take a square of Q n t, then what you get? You get I n t minus 2 upon n t L n t L n t transpose plus 1 upon n t whole square. You get L n t L n t transpose, again you get L n t L n t transpose. Now, L n t has all elements equal to 1. So, L n t transpose L n t is equal to n t. So, it is a scalar. So, you can take it outside and actually you get L n t transpose, and then you take n t outside, and one n t will cancel out. So, finally, you obtain Q n t. Therefore, Q n t is an idempotent matrix. It is symmetric also. If you take transpose of Q n t, it is equal to Q n t. Further, if you post multiply Q n t by L n t, then what you get? Q n t L n t is equal to, first you have I n t here multiplied by L n t. So, you get L n t minus 1 upon n t L n t L n t transpose L n t. Again L n t transpose L n t is equal to n t. So, you get L n t minus L n t, which is equal to 0. Then if we pre-multiply y by Q n t, it gives y as deviation from mean. So, suppose you take y vector, then L n t transpose y divided by n t gives you say y bar, the mean of all the y's, and Q n t y is then equal to Q n t is equal to I n t. So, you get y here minus 1 upon n t L n t, we take 1 upon n t here, then L n t transpose y. Now, 1 upon n t L n t transpose y is equal to y bar. So, you write y bar here. So, now you get a vector with y vectors as deviation from mean. All the elements are taken as deviation from mean. Then, if we pre-multiply equation 2 by Q n t, this is your equation 2, then you get Q n t y equal to, now the first term vanishes. If you multiply by Q n t, then Q n t L n t is equal to 0. Then you get Q n t x beta plus Q n t u. Further, in this model, for expectation of Q n t u u transpose Q n t transpose is equal to sigma square u. The variance covariance matrix of u is expectation of u transpose equal to sigma square u I n t. So, you can take sigma square u outside, then inside you get q n t transpose. Then q n t transpose is equal to q n t. So, you get q n t square, again q n t is idempotent. So, you obtain q n t here. So, the variance covariance matrix of this disturbance term is sigma square u q n t. Now, we apply generalized least square to model 4, and then it gives you the following estimator for beta b equal to x transpose q n t x inverse x transpose q n t y. So, in the model y equal to x beta plus u, if the variance covariance matrix of u is sigma square u omega, then the GLS estimator for beta is x transpose omega inverse x whole inverse x transpose omega inverse y. Further, q n t is an idempotent matrix. So, q n t inverse is actually q n t. So, you get the expression for GLS estimator as b equal to x transpose q n t x inverse x transpose q n t y. Now, this estimation method is the simplest one, but it is not appropriate, because we are assuming that the observations are IID. So, we have ignored panel structure of the data. You have simply taken as your model as a multiple linear regression model. You have assumed that these disturbances U's are IID. So, we have completely ignored the panel structure of the data. Now, we consider one way error component regression model. Again, we consider the model y I t equal to alpha plus x I t transpose beta plus u I t, or you can write it as z I t transpose delta plus u I t, where delta is alpha beta transpose whole transpose. So, actually delta is like this alpha beta, and then z I t transpose is equal to 1 x I t transpose. Then we specify the following error structure for u I t. So, u I t is equal to mu I plus eta I t. Here mu I is time invariant, it does not depend upon t. For all values of t, mu I is constant for a particular I. So, it is actually time invariant, and it accounts for individual specific effects. So, mu I, this part of the disturbances accounts for the individual specific effects, the effects corresponding to different cross section units, different i's. Then we take summation I equal to 1 to capital N, mu I equal to 0 to avoid perfect multicollinearity. Say, if you do not take summation I equal to 1 to N, mu I equal to 0, then you face the problem of multicollinearity, because you have this intercept term also. Then we also assume that eta I t is uncorrelated with x I t. So, all these explanatory variables are uncorrelated with eta I t, but so far we have not taken any assumption about the correlation between x I t's and mu I. Now, the disturbance term actually has two parts. Mu I varying across individuals or cross section units, which may or may not be correlated with explanatory variables x I t. This part mu I, it does not involve t. So, it is not varying through time, but it is varying across individuals or across cross section units. And so far we have not taken any assumption about its correlation with excites. So, it may be correlated with excites or it may not be correlated with excites, the explanatory variables. Then the second part is eta I t. Eta I t varies across individuals as well as through time also. And then we also assume that this is varying independently, means different eta i's t's are I d. It involves I as well as t. So, that is why it is varying across individuals and time. Now, we can write the model 5 as y equal to alpha L n t plus x beta plus u, where u transpose is equal to u 1 1, u 1 2, so on u 1 t, u 2 1, u 2 2, u 2 t, so on u n 1, u n 2, u n t. Further, we can write 6 as, this is your equation 6, u I t equal to mu I plus eta I t for all I equal to 1 to n, t equal to 1 to t. So, now we write all UITs in using matrix and vector notations. So, we write u equal to d mu plus eta, where d is equal to I n canonical product L t. So, actually d is the selection matrix of ones and zeros. If you look at the detailed expression for d, it is somewhat like, say you have 1 1 1, then 0 everywhere, and then you have 0 0, then you have another t elements 1 here, all other elements are 0 and like this. So, this is your t. Then mu is equal to mu 1 mu 2 mu n transpose, and if you multiply mu by d, then this d works like a selection matrix, means say for first t elements for I equal to 1, you get mu 1, this d mu selects mu 1. Then for next t elements, means for I equal to 2, it selects mu 2 from here and so on. So, this is a selection matrix. Eta transpose is equal to eta 1 1, eta 1 2, so on eta 1 t, eta 2 1, eta 2 2, eta 2 t, so on eta n 1, eta n 2, so on eta n t. Then J t is T cross T matrix with all elements equal to 1. So, obviously, L T transpose is equal to J T. Then, if you take D D transpose, D D transpose is equal to D is equal to I n canonical product L T, and then you have D transpose. So, I n canonical product L T transpose. So, this is equal to I n canonical product L T L T transpose, and L T transpose is equal to J T. So, you obtain I n canonical product J T. Further, D transpose D is equal to I n canonical product L T transpose L T, and L T transpose L T is equal to T. So, you get T times I n. D transpose D is equal to T times I n. Now, the projection matrix of J T is P D equal to D, D transpose D inverse T transpose. Then obviously, D transpose D is equal to 1 upon T I T. So, actually D transpose D inverse is 1 upon T I T. So, you get D transpose D inverse D transpose equal to 1 upon T D transpose, and then D transpose is equal to J T, and then we are writing 1 upon T J T equal to J T bar say. Further, we take Q D equal to I n T minus P D, and then y bar I is equal to 1 upon T summation T equal to 1 to capital T y I T. So, actually this y bar I is the mean of observations on y's corresponding to the ith individual or corresponding to the ith cross section. So, this is actually individual mean. Then, if we take Q d y, then Q d y is equal to y minus P d y, and then P d is equal to 1 upon T J T or J T bar. So, you get y minus 1 upon T J T y. Now, if you look at this J T y, then what it does? It adds, say, for the first individual or for the first cross section, it adds all the observations, and then we are dividing by T. So, you get y 1 bar, then it adds all the observations corresponding to the second cross section, and then again you are dividing by T. So, you get y 2 bar and so on y n bar. So, basically Q D obtains deviations from individual means. Then both P D and Q D are idempotent symmetric matrices. If you multiply any vector by Q D, then you get the deviations from individual means. Then now we consider random effects and fixed effects model. In panel data models, examine cross sectional or group and or time series effects, and these effects may be fixed or random. In fixed effects, we assume that individual groups or time have different intercept in the regression equation. Normally, we take different intercepts for the individual groups or different intercepts for different cross sections. Random effects assume individual group time having different disturbances. Again, usually we assume different disturbances for different groups. Now, first we consider fixed effects model. The individual specific effect is a random variable allowed to be correlated with explanatory variables. Say suppose you have this individual specific effect mu I, then mu I varies across individuals. It is a random variable and it is correlated with XIT. In fixed effects model, we assume that mu i's are correlated with XITs. Then remainder disturbances eta IT or IIT having mean 0 and variance sigma square eta. So, all these eta ITs are IID random variables having common mean 0 and common variance sigma square eta. Then the fixed effects models provide a proper description if the objective is restricted to making inference about the behavior of a fixed set of n, say firms or n individual units and cross sections, means your cross sections are fixed. For example, suppose you have fixed number of firms, say suppose you have just 4 firms and then you want to develop some model for these 4 fixed firms. So, your individual units, individual firms are fixed, or if we want to make inferences and develop model for SAARC countries. So, again your individual units are fixed, your cross section units are fixed. So, in that case fixed effects model provide a proper description. Or suppose you want to develop some model for Indian states. So, your different cross section units are different Indian states, and then for different states you have time series observations and you want to develop some model. So, in that case again your cross section units are fixed, you have fixed number of cross section units, and then you can use fixed effects model. Random effects model. Now, in panel studies usually capital N is large. Now, if capital N is large means if number of cross section units is very large, then a fixed effects model has a large number of parameters, a large number of mu i's, and then this leads to enormous loss of degrees of freedom. And since you have a large number of parameters, the efficiency of your estimates will be affected. Your estimates may not be very efficient. Now, in random effects model, the individual specific effects mu i's are taken as random variables, and we also assume that these mu i's are uncorrelated with the explanatory variables XITs. So, in random effects model we assume that XITs are independent of mu i's and eta ITs for all I and t. Say we assume that mu I follows some IID distributions. These mu i's are IID random variables having mean 0 and variance sigma square mu, and eta ITs are also IID having mean 0 and variance sigma square eta, and we assume that mu i's are independent of eta IT. Then random effects model is an appropriate specification if we are drawing n individuals randomly from a large population. Say suppose you have a large number of cross section units and then you are drawing a sample of say capital N individuals randomly from that large population, and then you are taking observations on those capital N individuals only. Then you can use random effects model. In fixed effects model, when we use fixed effects model, when you have a fixed number of cross section units, say different states of India, and you are taking observations on all the states. So, you have fixed number of cross section units, and you are not selecting a sample from the states, you are taking observations on all the states, but here you have a large number of cross section units. So, you want to draw a random sample from that large population. So, you are drawing n individuals randomly, then on n individuals you are taking observations. For example, in household panel studies, we draw a random set of households as cross section units. So, initially what we do? We draw a random set of households, and then these selected households are your different cross section units. And then for these cross section units, these selected set of households, you take time series observations. Then in random effects model, individual effect is characterized as random. We assume that mu i's are random variable. Then inference relates to the population from which this sample was randomly drawn. So, although you have a large population and then you are drawing a set of capital N individuals, but your inference actually final inference relates to the population of all the individuals from which you have taken the sample. Then one has to be careful that the selected group of cross section units should be a proper representative of the population we are interested in. So, this is important, very crucial. You have selected a particular sample from a large population, and then you are taking observations on this selected group, and then you are fitting model for this selected group. So, this selected group should be a proper representative of the population we are interested in, because finally you are drawing conclusion about the entire population. Now, if you think there are no omitted variables, or believe that the omitted variables are uncorrelated with the explanatory variables that are in the model, then prefer a random effects model. So, if there are no omitted variables, or even if there are some omitted variables, you believe that those variables are uncorrelated with the explanatory variables. So, in that case, even if you have taken observations on all the possible cross section units, you have not done any random selection from the cross section units, even then you prefer a random effects model. Now, if you think that there are omitted variables and these variables are correlated with the variables in the model, say you have omitted some of the variables and those variables you believe that may be correlated with the explanatory variables included in the model, then fixed effects model may be used for controlling the omitted variables bias. So, in that case one should go for the fixed effects model. But the omitted variables must have time invariant values with time invariant effects. So, those variables must be time invariant, or their effect must be time invariant. Then random effects model assumes exogeneity of all the regressors with the random individual effects. So, we assume that all the regressors with random individual effects are exogenous variables, whereas fixed effects model assumes endogeneity of all the regressors with the random individual effects. Now, we consider estimation of fixed effects model. First, we consider two period model. So, we consider two period panel data fixed effect model y I t equal to x I t beta plus z I delta plus u I t, t equal to 1 2. So, t takes just two values. We have two period panel data model. X I t is matrix of explanatory variables that varies across time and individuals. Then Z I is the matrix of variables varying across individuals, but for each individual constant across the two periods. So, this matrix of variables Z I does not depend upon t, it does not involve t. So, it just varies across individuals and it is constant across the two time periods. Then we write u I t equal to mu I plus eta I t. Further, this mu I t is individual specific, means it does not depend upon t. Expectation of eta is equal to 0 and expectation of eta transpose is equal to sigma square eta I n t. Here t is equal to 2. Expectation of mu I is also taken as 0. Then expectation of mu I mu j is equal to 0 for all I not equal to j, and expectation of mu I square is equal to sigma square mu. Further, we assume that expectation of mu I eta j t is equal to 0, and all these expectations are conditional on x and z. Now, suppose we write w I t equal to x I t z I. Then for fixed effects model, we assume that expectation of w I t transpose u I t is not equal to 0. And why you get this kind of correlation? It is just because of mu I. Mu i's are correlated with the covariates. Now, for observing the effect of violation of this orthogonality assumption, we consider the OLS estimator for the first period data. Say, suppose you take this first period data y I 1 equal to x I 1 beta plus z I delta plus u I 1, and then we write it equal to w I 1 gamma plus u I 1. Actually, we have taken gamma equal to beta delta. So, you get y I 1 equal to w I 1 gamma plus u I 1. Then expectation of w I 1 transpose u I 1 not equal to 0, because these w i's are correlated with the disturbance term, and then this implies that the OLS estimator of gamma is biased and inconsistent. So, if you apply OLS to the first equation, for estimating gamma, then the OLS estimator is biased as well as inconsistent. And then if you consider the second equation, say y I 2 equal to x I 2 beta plus z I delta plus u I 2, and then you write it equal to w I 2 gamma plus u I 2, then the same problem you have with the second equation also. In the second equation also, w I 2 is correlated with u I 2. And why you get this correlation? Because z I is correlated with mu I. So, again if we apply the OLS procedure for estimating gamma, then the OLS estimator is biased as well as inconsistent. So, as such you cannot apply the OLS procedure for estimating the parameters of panel data model, because these z i's are correlated with mu i's, and because of this correlation these w i's are correlated with u i's, and then this correlation leads to biased and inconsistent OLS estimators. Now, suppose you take the difference, say y I 2 minus y I 1, then y I 2 minus y I 1 is equal to, you get x I 2 beta plus z I delta plus u I 2, and then we write u I 2 equal to mu I plus eta I 2, and then you have y I 1. Y I 1 is x I 1 beta plus z I delta plus mu I plus eta I 1, and then we take the difference. So, y I 2 minus y I 1 is equal to x I 2 minus x I 1 beta, and then this term will cancel out. Further, you have mu I minus mu I. So, again mu I will also cancel out, and then you have eta I 2 minus eta I 1 here, or you can write it as say delta y equal to delta x beta plus delta eta. So, you get this model in the first differences. So, basically what you are doing, you are taking the first differences, you are transforming the original model into this model by taking the first differences, and when you take the first differences, the terms involving delta and mu I, these terms drop, because these terms are time invariant. So, now your problem is resolved. Now, this term is uncorrelated with delta eta, and you can apply OLS procedure for estimating beta. So, if you apply OLS procedure, then you get consistent estimator for beta. But one thing you must notice that you cannot estimate delta, or you cannot even estimate mu I, or if you take the first differences, if there are some x's which are not correlated with mu's, but which are time invariant, means if there is some particular variable, say x I t, say for some specific value of k, say for k equal to 3, suppose this variable does not depend upon t, means x I 1 3 is equal to x I 2 3. Then if we take the first difference, then that particular variable or the effect of that particular variable will also be omitted. So, this variable also drops out. So, the variables which are time invariant, even if those variables are not correlated with mu i's, also drop out, and you will not be able to estimate the corresponding regression parameters. So, in the previous model, since expectation of delta x, delta eta is equal to 0, we can apply OLS to estimate beta, and the resulting estimator is unbiased and consistent. Then with fixed effects estimators, we cannot recover estimates of any time invariant explanatory variables. As I mentioned earlier, if you have any particular variable, say x I t 3, which does not depend upon t, means x I 1 is equal to x I 2 3. So, this particular variable is time invariant, then we cannot recover the estimates of this particular variable. Then removing effect of unobserved correlated effects mu I through the differencing, the effect of observed time invariant explanatory variables is automatically removed. So, this is one of the problem. Then fixed effect estimator is robust to the omission of any relevant time invariant explanatory variables. So, obviously, suppose there is some time invariant explanatory variable which should have been included in the model, but you have by mistake omitted that variable, you have not included that variable in the model. Then when for obtaining the fixed effects estimator, when you take the first difference, the effect of that particular omitted relevant variable will not be there, or you can say that your estimator is robust to the omission of any relevant time invariant explanatory variables. When random effect model is valid, that is, if z i's are uncorrelated with mu i's. So, you can use random effects model. Even then, if you are using fixed effects estimator, it will still produce consistent estimators of identified parameters. So, you can still estimate beta using the fixed effect estimator. Then the orthogonality condition is still satisfied when random effect model is correct model. So, even if the random effect model is your correct model, still you can use the fixed effect estimator, and the estimator is consistent. But in this case, the random effects estimators are more efficient than the fixed effects estimator. So, although even if the assumptions of random effects are satisfied, you can still use the fixed effects estimators, but you are going to lose efficiency of the estimator. So, in that case, one should go for the random effects estimator. Further, here we have taken a particular transformation, we have taken the first difference. You can use some other transformation also, you can use any transformation which omits the effects like z i's or mu i's. So, which omits these time invariant effects. Although here we have considered just the first differences as the transformation. So, in this lecture we have discussed a panel data model with one way error component. We have discussed both the fixed effects model as well as random effects model. In particular, we have discussed the estimation of fixed effects model when you have two time periods, means t takes two values, t equal to 1 and 2. We observe that because of the correlation between some time invariant variables and the random component mu I, if we directly apply the OLS procedure, the resulting estimator is inconsistent as well as biased. To resolve this problem, one can use some transformations, like we have taken the first differences and then the resulting estimators of parameters are consistent. But a problem with such kind of transformations is that you cannot recover the effects which are time invariant, means you cannot estimate the regression parameters corresponding to the effects which are time invariant. Here in this lecture we have considered fixed effects model with two time periods. In the next lecture we will extend the estimation of fixed effects model for more than two time periods. We will also discuss the estimation of random effects model. So, I am going to stop here. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.